Continuing my discussion on tire light models, I wanted to circle back to the question, can photons decay in redshift, either spontaneously or inherently due to some mechanism that's built into the way photons function? And to understand that, we really have to have a model of the photon first. And I like using the de Broglie model for this, because photons have a rotating electric and magnetic field that goes with their motion. And de Broglie realized that we can actually think of this as a real field, and a rotating electromagnetic field behaves like it has a dipole in the middle that's rotating. And I'm not one for imaginary physics, so if a rotating field requires a rotating dipole in the middle, then there's a rotating dipole in the middle. And as the dipole rotates, it produces an electromagnetic field in its plane of rotation and a magnetic field perpendicular to it. And de Broglie realized you could have a realistic model of the photon if you have a new dipole each half wavelength, alternate rotating, and you get the field that propagates. And each of these dipoles is essentially an electron-positron quantum fluctuation in his model. Although I think it could be any other quantum fluctuation that's a charged particle pair dipole. But electron-positrons would be the norm. So given that model, we then have to ask the question, does it take energy for the field to propagate? Well, absolutely. Because as it propagates through the quantum field, which is polarizable, which means it also has dipoles, these dipoles in the field have to rotate as it gets polarized into space. And their rotation requires energy. So half of the energy of a photon is in its field. And this is something that Einstein and Hopf realized back in 1910 when they were first studying zero-point field theory and the consequences of it. That when a body moves, we think of its kinetic energy as being mass times velocity squared. 1/2 mass times velocity squared. But in reality, there's another half of the energy in the inertial field around it. And in electromagnetic conditions, we have that as well. And this problem has caused many physicists to make a factor of 2 error in the calculations, because it works fine if you want to use half the energy all the time or use all the energy all the time. But if you mix up the two, then you get errors in your calculation. Now the question occurs that I thought about and written about is, what happens when a photon gets absorbed? What happens when it gets hit and it excites an electron in some substance, say a detector, and we detect it? If you look at the light cone, which is normally drawn at 45-degree angle, the electromagnetic field is mostly outside of the light cone, which means it has to travel faster than the speed of light, the energy does, in order to get back to the detector at the point where the photon was absorbed. How does it do that? Well, if you're looking at producing an electric field, you don't need to rotate 180 degrees to produce an electric field. You only need to move a fraction of a degree. So the field can propagate outward much, much faster than the speed of light if you're using a quantum field, polarizable field model for electric fields. And magnetic fields are similar. You're just looking at the rotation in the perpendicular direction. So these fields can, and obviously do because we see it, collapse faster than light. But no physically real process is perfect. So the speed of collapse can't be infinite. It can't be instantaneous. Even though the way we have a non-model of photons in standard physics just assumes that it's instantaneous without saying so, because it's supposed to be limited by the speed of light. So it can't be instantaneous. But in any realistic model, it has to be instantaneous, or nearly so. But nothing's infinite. So if it's not infinite, does energy get lost? Is this a possible mechanism for tired light? Well, maybe. I don't know. It's something I've been thinking about for some time. But if we go back to the Broglie model, you have a dipole rotating each half wavelength, which means it generates a brand new electric and magnetic field each half wavelength. So it propagates outward and propagates inward. So if those rates of propagation are equal, not infinite, but equal, then we don't have a problem. We don't lose any energy. And I think this is likely what's happening. That even though we can't have a perfect process that's infinitely fast, we have an imperfect process that is still very fast, but doesn't lose energy. But if we think about, okay, what if it does lose energy? Because we do see redshift, so there has to be a mechanism. So what if this is related? And well, the energy has to go someplace. In order to lose energy, the energy has to go somewhere. Something else has to pick it up. And if we think about where it could go, well, you're talking about electromagnetic fields and being orphaned in space somewhere. Maybe a charged particle could pick it up, an electron or a proton. And maybe it can change its kinetic energy. And that's where the energy could go, perhaps. Or something more complicated, like an atom, like hydrogen. It's not enough energy to make orbital transitions happen with electrons changing their distance from the nucleus. So it'd have to be some other form of energy. And again, you get back to kinetic energy. And you can think of dust or larger matter. And again, you need some form of kinetic energy, some interaction. And I would throw out possibly my general relativity idea. Or we could step back and say, well, what if it's exciting the quantum fluctuations in the quantum field? That the electromagnetic field hits a quantum fluctuation and gives it some energy, which would convert it into a photon. But those photons would be extremely low energy, much lower than the cosmic microwave background. So I don't even think that we'd have a way to detect photons at that low of an energy. But maybe. If we could, that would be interesting. So those are a couple ideas. Do I think photons are decaying? No. I think that the amount of energy spent to produce the electric and magnetic fields propagating outward and collapsing inward are opposite but equal, and no energy gets lost at the detector or anyplace else. So I don't think this is the real mechanism by itself. But I wanted to talk about it and get people thinking about tired light redshift from a standpoint of having a real physical model to work from. So I hope you enjoyed this video, and if you do, please like, share, and subscribe. And I do discuss this model and problem in my book, The Zero Point Universe, which I have for sale, along with a couple other books. And I'd like to thank my PayPal, Patreon, and Super Thanks supporters. You're a big help to me, and thanks to everyone else for watching.